My name is Abhijit Gole. I'm going to walk you through some of the technical details of these three products. So let's start with what is this DragonFly? On the face of it, it looks like a PCIe SSD. And I get asked this question all the time, is it a PCIe SSD? And my answer is not quite. It is something slightly different. We like to call it a family of PCIe card solutions designed for storage system developers and application developers. I call it solutions, but what they are really they are building blocks. And this is sort of the key message I want you all to take away today from this presentation, that these are powerful building blocks for building the next generation system level solutions for storage. And I think that it is very important to have these kind of building blocks for the next generation, because as you know, we are moving towards what is clearly software-defined storage and software-defined data centers. So these kinds of components, that are powerful building blocks, are what are essential for that kind of void. Now, what makes them actually powerful is something I hope that you will appreciate as we go through the course of this presentation. So we offer these products in two classes or two modes of operation. One is the store mode, and the other one is the cache mode. And the intended use cases for sort of different tiers of system level solutions. So we intend the store mode to be used in a particular tier of solutions, and the cache mode in a different tier. And as we go through the presentation, I hope you'll appreciate what that is about. Any questions? OK, so let's start with the first building block, the DragonFly NVRAM. So the NVRAM is the sort of flagship product, but it's also the base on top of which we build the other products. It is a store class product, and it's specifically aimed at storage system designers and appliance vendors. As Mark mentioned, it's got this large SODIMM on it. It can be variable size. We support 2 GB, 4 GB, and 8 GB of DRAM capacity. And it's got those two hold-up supercapacitors. Those supercapacitors provide the hold-up power when the card loses power, and they power the card long enough for us to safely store all of that data in the DRAM into NAND flash. So there is NAND flash on the back side of the board where we do that. So one question that you may ask is, why such a large NVRAM? You may have known other storage systems where typically the NVRAM sizes are much smaller. Actually, just for some background, in my previous life, I used to be very deeply involved in the architecture and design of NVRAM systems at NetApp. So I have a lot of perspective on NVRAM. And what I've come to realize is what NVRAM can be used for, and this was something that I had even proposed while I was at NetApp almost like 10 years ago, but I think that's coming to reality now, is that you can actually use NVRAM for metadata. Traditionally, it's been used more as a log, but you can actually now potentially use this for metadata. So why metadata? As you know, metadata is very important in most storage systems and databases and all of these kinds of applications. Actually, metadata is critical to most systems. And as you know, metadata is bits of information that actually describes the data. But there are some unique properties to metadata. Metadata can be somewhat evil to deal with. And why is that? I mean, why do we think metadata is evil? Because it is different in characteristic in how you handle metadata than data typically. So what's evil about it? Well, for one thing, it's treated more like memory. You're going to access it in bits and bytes. You know, you're accessing data structures, usually in-memory kind of data structures. And you want to update them very frequently. Typically, these kind of data structures are, you know, bitmaps or hash tables or, you know, radix trees, B trees, all kinds of data structures. But if it was all in memory, it wouldn't be such a big problem. It's the next property, which is the need for persistence, that makes it much more challenging to deal with. Because all of that metadata is sort of critical to describing the data. So if you can't keep that persistent, then you've pretty much lost the data. But it gets worse. Metadata not only needs persistence, but it needs certain ordering in its update. You need to guarantee that certain bits of metadata are updated only after certain other bits. And sometimes you have to do that atomically. So that complicates things further. Even worse, you need to do these kinds of things at very high speed, very low latency. Latencies that can be in like nanoseconds to microseconds of access time. Keeps getting worse. It can be significantly large, you know, many, many gigabytes. So how do existing systems deal with these challenges? So existing databases, file systems, these types of systems, their typical mode of operation is to keep a volatile copy of the metadata in main memory, then log or journal the changes to the metadata in an on-disk log or a small NVRAM log, and then asynchronously apply those changes to the metadata that's on disk. More modern database systems like NoSQL databases or key value stores that are being used for big data, they're doing things slightly differently. What they're doing is they're taking the log data, they're logging the data and the metadata together in a single update to disk, which ends up creating a nice sequential access pattern. But over time, those logs fill up, and then you have to do a lazy garbage collection of deletes and overwrites that go into the log. So what is wrong with this existing handling? So there is a key assumption in both of these ways in which metadata is handled. And that key assumption is that updates and deletes are infrequent. They're not happening very frequently. And I think that key assumption may or may not be true, right? I think in many cases it's not true at all. For example, you might be familiar with NFS and the no A time option. The no A time option is required because most file systems will update the access time field in the inode every time you read or write or do any operation on that file. And that can become a serious performance bottleneck. So what people do is they use this no A time option to turn off all kinds of access time metadata updates. That results in better throughput or better performance, but you're actually losing information. You're losing access time information. So it's just a workaround. It's not a real solution. There's also, in file systems, a problem of handling millions of file creates and deletes at speed. That also involves lots of metadata operations. So similar patterns are now emerging even in the big data world. So both traditional and the modern NoSQL log-based systems cannot deal with these kind of access patterns very well, because their throughputs will drop because of all the asynchronous log handling that needs to be done. So clearly something needs to be done for the future where we need to get away from this log-based mechanism and see if we can actually make the metadata itself non-volatile, so that we can do all these metadata operations directly to non-volatile memory. And I think that's where things like SSDs could make a difference. But are the currently available SSDs good enough for this problem? So let's take a look at SSDs. What about byte level access? Most SSDs don't provide you byte level access to data on the SSD. For repeated overwrites, NAND flash is actually especially bad with repeated overwrites. It is non-volatile, so it's got that. Ordering, most SSD interfaces will not permit any kind of ordering. That is left up to the application. So if you need ordering, then the application has to issue a write, wait for that write to complete, and then issue the next write. So that slows down your performance. Some SSDs do support atomicity, so it's got that. What about speed? Speed can be good, but it's variable, not very consistent. It can range from tens of microseconds to hundreds of microseconds, or sometimes go into milliseconds. Capacity, it's good on that. It can be hundreds of gigabytes to a terabyte or more. So are they good enough? Perhaps. But I think clearly we can do better. So let's take a look at what DragonFly NVRAM architecture does and how we can address some of these issues for metadata. So if you look at the DragonFly card that you have right now, essentially it's a PCIe card, so the host is talking to the card over PCIe. There's two main components on the card. There's the ASIC right here, and the DRAM. Of course, there's the supercap and the NAND flash on the back to protect this DRAM. But if you look inside the ASIC, what you'll see is a bunch of powerful DMA engines that can move data from host memory into this NVRAM at very high speed. We've got a command delivery engine that can be used to deliver I/O commands as well as control commands to that CPU that's in that ASIC. It's a powerful ARM CPU we have there. But you also have this ability for the host to access the NVRAM directly by memory mapping that memory. So what does that give you? So the command API that is available through this command delivery engine can give you all kinds of control. It's possible to implement some of the things that I've been talking about in terms of ordered writes, more powerful operations like compare and swap. So you can build and implement systems where metadata is directly in NVRAM, and you can access it and modify it at very, very low latencies. The memory mapped interface allows this sub-microsecond access latencies. Again, it can allow you to directly modify metadata. And for block movement, if you have large bits that you want to move back and forth, we have these powerful DMA engines that give you upwards of 600K IOPS and like 3.2 gigabytes of per second of throughput. So all of that really makes it possible for the next generation system designers to think of putting metadata directly into NVRAM and operating directly on that NVRAM instead of having to do things like create a log or a journal and then apply that over time. So those are some of the key benefits of NVRAM. And we find our customers are asking for more and more of these capabilities now that they know that we have this architecture where we can extend it in terms of the kinds of ways in which we can modify data at byte granularity or in an ordered way and things like that.